Okay, so good evening, everyone. Welcome to the ninth live session for the course Advanced Reinforced Concrete Design offered by NPTEL. I am Arshit Agarwal, a PMRF scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for the entire course duration. So, in today's session, we will first have a recap of week 8 of the course that we concluded last week, and then we'll have a quick review of week 9 content. So, the week 9 recordings they were oriented towards understanding the compression behavior of reinforced concrete column. So, in this today, we'll start with having a basic overview of reinforced concrete column, understanding the classification of columns in terms of its definition, dimension, shape, and size. Then we'll discuss about effective length of column, what are sway and non-sway frames, and how for a given frame structure we estimate whether it's a sway frame or a non-sway frame using stability index factor calculation and lateral flexibility calculation. So those calculations we'll see. Then we'll see how to read alignment charts for predicting the K value for effective length. And after this, we'll see IS 456 provision for design of reinforced concrete column. First discussing about tight columns, and then at the end, we'll see about spiral column and the additional strength that comes due to confinement effect. So in total, along with the quick theory recap of different segments, I will introduce you with several questions to challenge your understanding. We will have around 6 to 7 questions in total. There will be some numericals and some theoretical questions. And at the end, I will make myself available to solve any queries related to assignments and the discussion that we had today. That we'll have today. Okay, so let's start. So last week we continued our discussion about shear behavior of reinforced concrete by understanding the role of shear span to depth ratio in governing the failure mode. Whether the failure mode will be shear or flexure. So if this A by D ratio is small is less than point 0.2 is less than 2.5, we saw that shear failure will dominate as an arch failure. Okay, if A by D ratio is greater than 2.5 and less than 5, then we say that there will be both shear and flexure failure combined. And if this A by D ratio is greater than 5, that means that the load is acting very close to the midspan, then we say it will be the flexural failure that will dominate. Then we looked into how Mohr circles can be used for estimating principal stresses and saw how Mohr circle will change as the position of an element in a reinforced concrete beam will change when it is subjected to a uniformly distributed load. We discussed how concrete resists shear. So it's a combination of three actions. There is uncracked concrete in the compression zone, which resists shear crack. There is aggregate interlocking, which also resists shear cracking, and there is dowel action of this longitudinal rebars that also resists the shear cracking. So we related this to table number 19 of IS 456, where we saw that we need both percentage reinforcement area and concrete grade to estimate the concrete shear strength. We saw different types of shear reinforcement, mainly vertical stirrups that can be one-legged or two multiple legged. There are bend-up bars and there are inclined stirrups which are provided to resist shear. If concrete is not able to resist shear, then we need to provide additional shear reinforcements also to resist the net shear. Then we discussed about torsional behavior of reinforced concrete, what is torsion, types of torsion, and how failure in torsion appears. We discussed two theories, soft-fill analogy and thin-walled tube theory, to understand how we can estimate the maximum torsional stress in a circular or a rectangular section or in any arbitrary shaped member also when it is subjected to a torsional moment of T. We saw how torsional cracking appears based on skew bending theory and how shear and torsion they combine and why we need side face reinforcement and top reinforcement. We discussed IS 456 provision for torsional design. First, understanding how torsional moment is incorporated into equivalent bending moment in tension and compression side also if needed. In compression side, if the moment generated due to torsion it is more than the actual bending moment, then we need to provide reinforcement in the compression side also. And side face reinforcement also it is needed if the depth of the section is greater than 450 mm. We saw how transverse reinforcement design is modified to take into account the additional shear generated by torsion, and we saw how we design the area of stirrups and spacing of stirrups in these case. Okay, so this was everything that we discussed in the last session. So now we will start discussing about reinforced concrete column. Okay, so first of all, what are column? So if we go with general definition, column is a vertical member that helps to elevate the structure by carrying load from one floor to another floor. So simply saying, it provides our structure the elevation by connecting different floors. Okay, now if we look at technical definition as per clause 26.5.3.1 of IS 456, it says that a structural element with the ratio of height to least lateral dimension exceeding 3 is which primarily supports compressive load is defined as column. So this height h and the least lateral dimension, suppose I'm naming it as d. If this ratio is greater than 3, then we say it is a column, else it is a pedestal. Okay. Now, how these reinforced concrete column function as compressive member? So you can see in this figure, they carry the entire floor load from top to bottom. So if you see here, the column which are present at the second floor, okay, these columns, they will carry the roof load as well as their self weight. Okay, so we will design this column to carry the roof load and their self weight. Now, if we look at the column which are present at the first floor, so this will now carry the load of the second floor column also plus the load of first floor and their self weight. Okay, so net load will be carried by this column. So for that load, we will design the column. Then for the bottommost column, it will carry the entire load which is there above first floor. That is the load that is present on these columns plus the load of first floor and their self weight. Okay, and then this entire load will be transferred to the footing and then to the ground underneath. So we can see that how this column which is providing elevation to the structure is also helping in carrying load from one floor to another floor. Okay. Now, in terms of reinforcement detailing that we do in column, there are two types of reinforcement that we provide. There is main reinforcement, which are longitudinal reinforcement that run along the length of the column. So suppose this is my front view of the column. So there will be longitudinal reinforcement that will present along the length of the column. Okay. So they resist the axial and the bending stresses that is acting on the column. And apart from this, there are lateral and transverse reinforcement, which are also known as tie bars, which are provided along the lateral dimension of the column to hold the main reinforcement and prevent buckling. So these are my longitudinal reinforcement, and like this will be my lateral reinforcement. So what these are doing, they are holding these longitudinal reinforcement also in position, and they are preventing buckling of longitudinal reinforcement also. So what is this buckling action? We'll see in the next session when we will talk about long columns where bending can occur. Okay, so for such column, these tie bars, they ensure that the rebars are in position, they are not buckling. Okay, under lower load values. Okay. Now, columns can be classified into different types based on their shape, dimension, and loading condition. So, based on shape, there are three types of column. We have tight columns, we have spiral column, and we have composite column. Okay, so tight column, we can say it is a rectangular column where we are providing lateral ties like a rectangular shape, which are holding the longitudinal reinforcement. In spiral column, there are circular columns where ties are provided in circular shape, and these reinforcement are they are distributed. The longitudinal reinforcement are distributed along the entire cross section of the column. So among these two types, the choice what we need to use, whether we need to make a spiral column or a tight column, it depends from structure to structure, from the aesthetic demand or the availability of the area, and any other factors also can contribute. So you can see in this figure, in these figures, how the column appears. So these are tight column that you can see are rectangular in shape, and where we have longitudinal reinforcement, and these reinforcement are caged with the help of tie bars. Okay, and this is circular column, okay, which are present in between floors. Okay, apart from this, there are composite column also, where inside there is a steel section. Okay, this I section, a steel section is there inside, and outside we have a steel. It is covered by either concrete, plain concrete, or reinforced concrete. So in this case, you can see there is a steel section inside and there is reinforced concrete outside. However, in the circular case, you can see there is I section inside, I steel section inside, and plain concrete outside. And here you can see I section inside and reinforcement along with tie bars as a spiral reinforcement outside. Okay, so these are known as composite columns. Now, based on dimension, there are two types of column. There is short column and there is slender column. So short columns are generally stronger and they fail by crushing due to direct stresses. So in short column, the height of the column is small. Okay, so they won't buckle, they won't bend that much. So they will feel only when the concrete is crushing. Okay, due to this axial stresses that are applied on the column. And then the standard column which are of higher heights, and they are comparatively weaker compared to short columns. Why? Because these columns, they can buckle, they can bend due to loading also. Okay, so these bending stresses that are generated in slender columns, they govern the failure of a slender column. Now, how to classify whether a column is a short column or a slender column? So we classify it based on slenderness ratio, which is known as L effective by D. Okay, so in both the direction, x direction and y direction, we calculate the slenderness ratio, the effective length of the column divided by the dimension of the column. So if this ratio, slenderness ratio, is less than 12, then we say it is a short column. And if this ratio is more than 12, then we say it is a slender column. So suppose along one direction, along x-axis, the ratio is less than 12, and along y direction the ratio is greater than 12. So what we'll do, we'll design the column along x direction before as a short column, and along y direction we will design the column as a long column. Okay, slender column. Okay, so that for both of these, the design approach is different. Okay, so that's why we need this classification. Now, here, what is L effective? So L effectives is basically known as the effective length of the column, which is nothing but a factor k times the unsupported length of the column. Okay, so this is how we calculate L effective. Okay, there is a factor k multiplied by the unsupported length of the column. And what is this unsupported length? It is the clear distance between end restraint of the column. So we'll see shortly what is this unsupported length and how we calculate that. And effective length is the length of the column which is actually under the loading action. So this also we'll see later in the slides where we'll do the calculation part. Okay. And finally, based on the loading, there are two types of column: axially loaded column, where there is directly axial stress that is acting on the column without any bending. So this is my top view of a column. If my load is acting at the centroid, then we say it is an axially loaded column. Okay, and then there is a centrically loaded column where there is both axial stresses and bending stresses. Suppose instead of not acting at the center, the load is acting here at this point or this point. So what will happen? It is under axial load also, and this due to this presence of a small deviation from the central line, there will be some movement also that will be generated due to this load. Okay, so that's why we say there is both bending action in the column and there is axial load also acting on the column, and these columns are known as eccentrically loaded column. So there can be uniaxial eccentricity if my load is acting along one of the axis, y axis or x axis, then we say that there is movement along only one direction. And there can be biaxial eccentricities if the load is acting at some arbitrary point which is generating moment along both the axes. Okay, so that is known as biaxial eccentricities. So for all these three conditions, based on IS 456, we'll see how design is done. Today's focus will be on the axially loaded column design. Okay, and how we determine the effective length of the column. Okay, now just try to answer these three simple questions based on the classification of column that we have seen recently. And if you have any doubt in the part that we have discussed till now, that also you can ask. Any doubt in the basic classification part of column? Okay, if there are no doubt, just tell me the answer for question number one. A reinforced concrete column is subjected to axial load and uniaxial bending is most critical when. So what will be the answer for question number 1? Can anyone tell me? So there is an reinforced concrete column which is subjected to axial load also and uniaxial bending also, but it is not mentioned along which axis the uniaxial bending is acting. So you need to tell me what will be the correct option. Okay, whether it is along minor axis or major axis. And first of all, tell me what do you mean by minor axis or major axis? Does anyone know, or will it be the same in both the axes? Any idea?
Maybe for major axis.
Why major axis? Okay, so see, this classification of major axis and minor axis, na, it is done based on the moment of inertia. So you know moment of inertia, it has the formula I is equal to b d cube by 12. Okay, so if my b and d are different, so if my dimension of a column is different, okay, one is 300, one is 450, one side is 300 and one side is 450. So along one direction my b value will be 300 and d value will be 450, and along one direction my b value will be 450 and d value will be 300. So the along the direction where my moment of inertia is larger, we say that is major axis, major principal axis. And along the direction where my moment of inertia is smaller, that we say it is minor principal axis. Okay, so the axis which has lower moment of inertia, that is minor axis, it is weaker compared to the axis which has higher moment of inertia. Okay, because if the moment of inertia is smaller, it won't be able to resist bending that well as compared to an axis where the moment of inertia is higher. Okay, so that's why what will be the most critical direction, it will be the bend when bending axis collides with the minor principal axis. Okay, got the reasoning, what is major and what is minor principal axis?
Yes, sir, yes, sir.
Okay, so along minor principal axis, the stiffness is also lower. So if the stiffness is lower, design will be more critical. Okay, now try to answer the second question. A column is classified as axially loaded if. So when we'll say a column is axially loaded. Okay,
C.
okay. Any other guesses? Yeah, the correct answer is D, both A and C. So see, we talked about three classification of column. Okay, I will just place it on slides show mode. We talked about three classification of column: axially loaded and eccentric loaded, uniaxial and biaxial. So what happens when we are talking actual structures? It is not always possible that the load will act on this centroid. Okay, the load may be acting at some distance away from the centroid also. Suppose this is the point where the load is acting. Now what code says, if this eccentricity e, okay, eccentricity is known as the distance from the axis of the loading point. Okay, so if this e value is less than 0.05 times 5% of the dimension, okay, okay, if this is my dimension d, okay, this side, okay, I will term it at dx and this is dy. Okay, so if my e value is less than 0.5% of dx, then we can say that we can ignore this effect of eccentricity. We can assume that the load is acting at the center only, because this will generate a very small moment which we don't need to take into account. So that's why a column is considered actually loaded if eccentricity is less than 0.05 times the dimension and load passes through the centroid axis without with zero eccentricity. Okay, so both option will be correct. Got the point?
Yes, sir, yes.
Okay, now try to answer the third question. Which of the following combinations correctly represent the classification of column based on loading? So based on loading, what is the classification of column? Just on the last slide we
A,
saw.
A, A,
Okay, this is a
NPL.
very simple question. Okay, A. So you need to remember different classifications of column also. That is important to know. So that if anyone asks you how you are classifying a column, there are three categories based on shape, based on dimension, and based on loading. Okay, and for each of these classification, design is done differently. So we'll see today how design changes for a tight column and a spiral column. Then later on we'll see, today we are focusing on short columns, later on we'll focus on slender column also, and then we'll combine slender column with eccentric loading also. So for each of these category, the design methods are changing, so it is important for us to understand each of the types very carefully. Okay, any doubts in the discussion till now? Okay, so let's move ahead. So when we are talking about slenderness ratio formula, we talked that it is equal to L effective by day. So there you saw a term which was new, which we used. It was effective length. Now, what is this effective length? So effective length of a column, that is represented by L effective. It is the length of the column, of a column is the distance between the point of zero moment or the distance between the point of inflection. Okay, and it is an important design parameter for column because it determines the critical buckling load of a column. So when column undergoes bending, okay, so suppose this is my column and this is undergoing bending. Okay, so when it undergoes bending, suppose this is how it is undergoing bending. So there can be 2 points where the moment can be zero. Okay, in this column. So the points where the moment is zero, the distance between these 2 points, or the points where this curvature is changing its shape. So from this to this, the curvature is changing. So these 2 points are known. The distance between these 2 points is known as the effective length of the column, and the distance between these 2 points is critical for buckling of column, because beyond these 2 points there is no buckling which is happening. Between these 2 points only the buckling effect is happening. So that's why it is important for us to determine the effective length of the column. Okay, so uh, this length, effective length of column, it depends upon various factors. It depends upon the end conditions of the column, type of loading, and the material properties also. Okay, now how we calculate effective length? So for this we first need to identify the end condition of the column, where it is, whether it is a fixed support, pinned support, or a free support. For each of the for each of these cases, the effective length of the column can change, because it will determine how the column buckling is happening. Okay, for each case the buckling behavior of column will change. So that's why we need to know the end condition of the column. Then we need to calculate the effective length factor. So we know effective length is given by k times the unsupported length. Okay, so this factor k that we need to calculate. Okay, this is an dimensionless parameter, and this factor k, it also depends upon the end condition of the column. Okay, the type of support and the type of frame, on both it depends. Okay, then we need to determine this unsupported length of the column. So we saw there is a thing which is known as unsupported length of the column. So this, what is unsupported length? This is the actual length of the column between 2 points of zero moment. So we saw actual zero moment is present at the top and at the bottom. So this length, complete length of the column, it is known as unsupported length of the column. This is also a point where the zero moment is acting. So this is known as effective length of the column. And the actual length where the between the points where zero moment is acting, it is known as unsupported length of the column. And in the framed construction, suppose I have a framed structure. Okay, this is my columns, then there are beams, then there are again columns, and then there are beams. So in such framed structure, this unsupported length L is taken care as is calculated as clear distance between floor and shallower beam. Okay, so suppose this is my column and this is the beam that is present over the top of the column. So my unsupported and this is the floor. Okay, this is my floor, this is my column, and this is my beam. So my unsupported length will be this part. Okay, total height of the column minus the depth of the beam will give me my L naught value. So suppose there are two beams here. One is of a different depth and one is of different depth. So shallower depth means this beam. Okay, so this will be my unsupported length. Okay, not this. Okay, so it depends upon the beam also. The subtracting the beam depth, the shallower beam depth will give us the unsupported length of the column. Okay, now when we multiply this unsupported length of the column with the effective length factor k, we get the effective length of the column. So we saw when we were discussing effective length factor, it depends upon the end conditions of the column. So and by end condition, it is not just the kind of support, fixed support or the pin support that we are talking. It also depends upon the type of frame that we are dealing with. There are two types of frame. There can be a sway frame or a non-sway frame. So what are these? So a structural frame whose joints are restrained from any kind of lateral displacement by attaching a rigid element or by bracing are called braced or non-sway frame. So you can see in this first figure, okay, this is my RC frame, okay, and when I apply some lateral load on this frame from this side, due to the presence of the shear wall that is present behind these frame won't undergo any lateral movement, okay, or any lateral displacement. So such frame are known as braced frame or non-sway frame. They are not swaying due to action of lateral loads. Okay, however, if there is no shear wall present on this side, so what will happen? This frame will undergo lateral displacement also, and such frames are known as unbraced frame or sway frames. So if a structural frame is not attached to an effective bracing element but depends upon the stiffness of bending stiffness of a column and girders to provide lateral resistance, such frames are known as sway frame. So amount of lateral displacement that is happening in such frame will depend upon the stiffness of columns and the beams. Okay, so these things will dictate how much lateral displacement is happening in the frame. So such frame where there is no support to resist lateral displacement and the lateral displacement is governed by the stiffness of the frame elements, such frames are known as sway frames or unbraced frame. Now, how to judge whether a frame is a sway frame or an unsway frame? So for this, we use a calculation which is known as stability factor. Okay, so stability factor, it is given by this value q, which is summation of uh, vertical load acting on a frame times the displacement, okay, deflection of a frame upon summation of shear force acting on the frame times the height of story. Okay, so pu is the vertical load. Delta naught represents the deflection between the top and the bottom of the story. So suppose this is my story, okay, one story. So what is the deflection that is happening here relative to this? That will represents my delta naught. So upon action of lateral load, suppose the story bends like this. Okay, so this is my delta naught. Okay, the displacement between the bottom node and the top node. Okay, that is delta naught. Vu represents the shear. This is the shear force that is acting on the frame, that is Vu, and Lc represents the height of story. So this complete height of story is known as Lc. So we calculate this value Q, that is my stability factor for a story. For an entire story, we are calculating this value Q. If Q is less than 0.05, then we say it is a non-sway frame. It is a braced frame. So it is not undergoing any lateral displacement. If this Q value is greater than 0.05, then we say it is a sway frame or a unbraced frame. So it is undergoing lateral deflection. Okay, so based on this stability value, we can comment whether it is a safe frame or a non-safe frame. Okay, now in IS 456 code, we can find the value of K for some basic cases. Like as shown on this slide, we have three well-defined cases for based frame or a non-sway frame. So you can see when both ends are fixed, okay, rotate for rotation it is fixed, so we can see that the deflection profile will come like this. So the L effective value, it is zero point 0.5 times the unsupported length of the column. Then if one end is fixed and the other end is free, then we say that the L effective value is zero point 0.7 times L. Okay, if both ends are free for rotation, then we say L effective is equal to L. Okay, so And for any other case where we don't know the end conditions of the column, we say if it is a braced frame, then the k value will lie between zero point 0.5 to 1. So these two, zero point 0.5 and 1, these are extreme cases. Both ends are free for rotation, or both ends are free. Okay. Now there can be no other cases beyond these. Either one end is fixed, one end is free, both ends are partially fixed and partially free. So when both ends are partially fixed or partially free, then the k value will lie between zero point 0.5 and 1. So these two represents the end conditions. For any other case, k value will lie between zero point 0.5 and 1. Okay, until it is a braced frame. Okay, for unbraced frame the criteria changes. So if both ends are rotationally fixed, then for unbraced frame we say L effective value is 1.5 times L naught. If both ends are rotationally fixed, one end is rotationally fixed and other end is free, so you can see this is fixed and other end is free, then we say that L effective value is equal to 2L. Okay. And then when both ends are free to rotate, then we say that L effective value goes up till infinity. So in such case, there is no 2 points of zero bending moment that that you will be able to find across, even if the length of the column, effective length of column, goes to infinity, then also you won't find 2 points where the effective length, where the bending moment is zero. Okay. Now, these two cases are extreme cases for us, fixed and free. So any other case, it will be partial restraint cases only. So we can say the key value for unbraced frame, it lies between 1 and infinity. Okay. So again, uh, what we discussed here in these two slides, they were exact key values for some of the cases. However, if you see in IS 456 code, this is table number 28, I guess, of IS 456 code. So this is table 28 of IS 456 code. So you can see they have listed different basic cases. This is for non-sway frame and this is for sway frames. Okay. So they have given different frames. Okay. And corresponding to different frames, they have given the theoretical value of effective length. So these are the theoretical value that we saw in last two slides also. But what code says, it reports there additional column also, which is recommended value of effective length. Okay, so this is the theoretical value that we have seen, and this is the recommended value that we need to take. So you can see instead of zero point 0.5 L, code says that take 0.65 times L. Instead of zero point 0.7, take 0.8. For one, take only one. For one, take 1.2. So like that, for some cases, code says either to take, we need to take a greater value of k. Why is that so? Why code is recommending a higher value of k? So that we can have a design on a safer side. So to make a design much more safer, code says to increase the value of k. Okay, for some of the cases. So this is all from table 28 of IS 456. Now, for cases where we don't know the end conditions properly, we need to calculate the stability factor. Once we know the stability factor, we'll know whether it is a sway frame or a non-sway frame. So we can proceed along whether to calculate the value of k. So to calculate the stability factor, we need to know the vertical load which is acting on the story. We need to know the story shear, and we need to know the story height. Okay, so these three things we can easily get. Okay, vertical load we can get, shear we can get, and the height of the story we can get. But how to calculate the deflection delta naught between top and the bottom? Okay, so to calculate this deflection delta naught, we calculate the lateral flexibility of a story. Okay, so what, how much flexible one story is, that we need to calculate. Okay, and what is this lateral flexibility? It is a resultant of deflection of column rotation and girder rotation. So initially when we are talking about sway frame, we saw that discussion that the amount of lateral displacement that happens in a sway frame, it depends upon the stiffness of both columns and girders. So that's why we need to calculate the deflection due to column rotation and deflection due to girder rotation to calculate the lateral flexibility of a story. Okay, adding both will give me the lateral flexibility of the story. So once I know this lateral flexibility delta naught, I can calculate the stability factor S, and then I can check whether my frame is a sway frame or a non-sway frame. Now, for estimating the deflection due to column rotation, what course says that we need to assume that the floor girders are rigid. So in first case, I'm assuming that these girders, they are rigid. Only columns is undergoing deflection. So this delta will be displacement between the top and the bottom. So that will be represented by delta 1. And for one part of the column, okay, for above girder, the column which are present above girder, the deflection will be delta 1 by 2. Okay, so total deflection is delta, and for each column the deflection is delta by 2. Now we can see that such these columns are like a cantilever which are present. Okay, so the deflection for a cantilever beam kind of structure, we can write delta 1 by 2, it is vh cube upon 3ei. So this is how we write the deflection of a column. Okay, so this will give me the value of delta 1. Okay, now this is for one column. If we know all the columns that are present in a story, then the total deflection delta 1 will be nothing but vh cube upon 12 e summation of ic, summation of moment of inertia of each column. So higher is the inertia of column, lower will be the deflection in the column. Okay, so we have seen earlier also the axis along which inertia is more, the deflection is lower. Okay, that is more rigid for rotation. So that same thing you can see from here also. Delta 1 is equal to vh cube upon 12e summation of ic, and this summation will be determined by the total number of columns that are present in a story. Now, in the second case for calculating the deflection due to girder rotations, here we'll assume that columns are rigid, only girders are rotating in double curvature. So this is what we mean by double curvature. Okay, so like this, girders are rotating. So in this case, if we are applying a rotation of angle theta at the end, then the internal moment that will be produced for a girder, it will be 12 ei theta by L. Okay, now how we get this value? So if suppose I am giving a unit rotation, if theta is equal to 1, then from basic structural mechanics we have seen at the near end the amount of deflection that is generated, it is given by 12 ei by L, and at far end it carries half of this, so that is 2 ei by L. Okay, and if same rotation I will give at this end, then it will be 4 ei by L here, and 2 ei by L will be carried here. So total if I will sum, okay, then it will give me 12 ei by L. Now this value we have seen for a unit rotation. For a theta rotation, it will be 12 ei by L times theta. Okay, so that is how we got the internal moment reduced in each girder due to theta rotation. Okay, so total moment produced due to girder rotation on a story, we can write as 12 ei summation of ib by li. So this is my first beam. Okay, L is the length of this beam and I is the moment of inertia of this beam. Then this is my second beam, third beam, fourth beam, as so like this for the entire story. We will do the summation. Now external moment, if the shear is acting V, okay, on this story, then the external moment that is produced, it is V into H. Okay, due to this coupling action, V into H by 2 plus V into H by 2, both will add up to give me the external moment. So if I balance this external moment with internal moment, and I use this relation theta is equal to delta by H, then I will get delta 2 is equal to Vh square upon 12e summation of Ib by Li. So this will give me the deflection due to girder rotation. Now adding the deflection due to column rotation and deflection due to girder rotation will give me the total deflection formula. Okay, so this is my total deflection formula. Here I will take V common. I will take V common, and then I will take H square common. So we can rearrange this equation in this form. Okay, and once we knew this value of delta u by V, by calculating the net pu and by calculating knowing the length of the height of the story, we can calculate the value of q. If q is less than 0.05, we will say it is a non-sway frame. If it is greater than 0.05, we will say it is a sway frame. Okay, once we know whether it is a sway frame or a non-sway frame, what we'll do, we will calculate the value of k. So for calculating the value of k, IS code has given some alignment charts. Okay, so where we need to calculate beta 1 and beta 2 factors. For braced frame, beta value is given by this equation. I represents the moment of inertia, HS represents the height of story, and B represents beam, C represents column. So using this, we will calculate the beta value for braced frame, and for unbraced frame, we'll calculate beta value from this equation. So first, by stability index, we'll know whether it is a sway frame or unsway frame. Then based on whatever frame we are getting, we'll calculate the beta value. Once we get the beta value, we'll use the alignment charts that are given in IS code. So for braced frame, there is different set of curves that is given to us. We know the beta 1 and beta 2 value both are the same. Okay, so beta is equal to beta 1 is equal to beta 2. That is what code is saying. So once we get the beta value, suppose it is zero point 0.4, so zero point 0.4 and zero point 0.4 here, we'll draw horizontal and vertical line, and we'll get a rough estimate of k value. Okay, so that k value will help us to calculate the effective length of the column. Okay, so you can see for fixed support this value is zero point 0.5, for hinge support this value is 1. So whatever k value we'll get, it will be in between zero point 0.5 and 1. Similarly, for sway frame where lateral displacement can happen, we have different set of alignment charts that is given. So again, based on beta 1 and beta 2 value, we'll calculate the value of k. And in this case, k is varying from 1 to infinity. Okay, so based on whatever beta value we'll get the value of k, and that will help us to calculate the effective length of the column. Okay, so let's see the application of this entire theory, how to calculate lateral displacement, then how to calculate stability factor, and then how to calculate the effective length of the column. We'll see. So the basis of this numerical is the same as you saw in the NPTEL recording, but the values here are different. So there you talked about a non-sway frame. Here we are talking about a sway frame. So we'll see what changes it is coming. So we saw there the height of the story was very small, 3 meter. Now we are dealing with a story height of 10 meter. Okay, so let's see what is the difference that will come in this. Okay, just give it a thought how you will proceed on with this question. Just tell me what is will be the process of calculation, and then I will tell you the solution. So I will pause myself for a minute so that I can give you time for thinking. In the meantime, if you have any doubt related to the concept that we have discussed right now regarding stability factor, lateral displacement value, and alignment chart, you can ask. Okay, just give it a thought how you will proceed with this question. Then we will discuss. So can anyone tell me how we will proceed along with this question? What will be the steps that we need to follow? And just give me a rough idea. What will be the process? So the frame structure that you are seeing here, the values, the axial load, and the height of the story, such values are correspond. You can relate this well with what buildings that you find in metro cities, the high-rise buildings. So such values, the story height, the axial load capacity that is there, you will find in high-rise building cases. So this is a more realistic case that you are seeing here. Okay, especially for metro cities. And column, the grade of concrete also M40, M50. So generally in metro cities we prefer higher grade of concrete because of more loading acting on the structures. So what will be the first step towards the solution? What is the first step that I need to do? Can anyone tell me?
I think we go for to find lateral flexibility,
Yeah,
delta
so
1,
how you
delta
will
2.
find lateral flexibility? First step is you will
VH.
determine the unsupported length of the column. Okay, L naught.
Oh, sorry. Yes, yes, yes,
Okay.
yes.
So you know the story, the you know this entire frame. Okay. Just a second. You know this the story. What is the entire frame present on this story? Okay, you know the dimension of column, dimensions of beam. Okay, so from this you will calculate the unsupported length L naught. Okay. Now after calculating unsupported length L naught, what you will do ahead? So then we need to determine whether it is a sway frame or a non-sway frame, for which we need to calculate stability factor. Now in stability factor, we need to know the lateral flexibility of the column. So what we'll do, we'll calculate the flexibility of column as summation of displacement of columns and displacement of girders. Okay, so for this we need to calculate the net moment of inertia of column and net moment of inertia of beam. Okay, see in this question you can see columns are all of same dimension. Okay, what is the dimension? 300 cross 300. So across both x direction and y direction, the moment of inertia of column will remain the same. But beam is changing. In y direction, beam dimension is different. In x direction, beam dimension is different. So moment of inertia of beam will change in both x direction and y direction. For x direction, it will be calculated based on this b1, and on y direction it will be calculated based on this b2. Okay, so once I have this data of net moment of inertia of columns and net moment of inertia of beam, I will calculate the modulus of elasticity of column and beam. So I know the grade of column, grade of beam. So modulus of elasticity will be given by 5000 under root fck. Then knowing all the values, I will calculate the delta u by v. Okay, so we know the height of story, we know the lateral moment of inertia of column, we know the moment of inertia of beam, and we know the modulus of elasticity of column and beam. Okay, so we'll calculate lateral flexibility in x direction, we'll calculate lateral flexibility in y direction. Then we will calculate stability index in x direction, we'll calculate stability index in y direction, and we will compare whether it is less than 0.5, 0.05, or more than 0.05. Once we get whether it is sway or a non-sway frame, we'll calculate the beta value. So again, beta value will be different in y direction, beta value will be different in x direction. Once we calculate the beta value, we'll use the alignment charts to calculate the effective length of the column. Okay, so this is how we calculate the effective length. Once we know the effective length, L effective by D will give me whether it is a slender column or a short column. Okay, so this is the entire process. Everyone are clear with the process? Okay, so let's see now. So this is the frame that I have given to you. Okay, so if you make a elevation view of this frame, what it will look like, these are my columns, which is 300 cross 300. Then we have beam along y direction, which is uh, 300 cross 450. Okay, so depth of the beam along this y direction it is 450, and along x direction the depth of the beam is 600. Okay, so along y direction my l unsupported length will be 1000 times minus this factor 600, and along x direction my unsupported length will be 1000, the total height of the story, which is 10 meter. Okay, 10,000 minus this depth of the beam, which is 450. So this is how we'll get the unsupported length of the column. Okay, shallower beam depth we need to subtract along x and y. Okay, so that is what we have done. Okay, so for y direction, my beams will be which are running along x axis, and for x direction, my beams will be those which are running along y axis. So that's why in y direction we have subtracted 600, and in x direction we have subtracted 450. Okay, so this is my unsupported length in y direction, this is my unsupported length in x direction. Okay, now next step will be calculation of stability index. Okay, so I will just duplicate the slide and I will move ahead. Okay, so I will just move it on the side. So we know what is the formula for stability index. So I will just copy the formula. So I know stability index Q, it is given by this formula. Okay, so this value Q we need to determine. If this value Q is less than 0.05, we'll say it is a non-sway frame. If it is greater than 0.05, then we'll say it is a sway frame. Okay, now for this we need to calculate this delta naught by VU value, for which we have the formula that we have derived. It is this. Okay, so this formula, this we need to calculate first. Okay, so here what are the variables? First I need to know the modulus of elasticity of concrete and beam. Okay, so why we need to calculate separately from beam and concrete? Because grade of concrete is different, grade of concrete in columns is different, and grade of concrete in beams are different. Okay, so what is the grade of concrete in column? It is M50. Okay, so for M50 grade concrete column, modulus of elasticity is will be given by 5000 under root FCK. So 5000 under root 50 to the power 1 by 2. Okay, so this calculation it will come out to be 35355.34 MPa. Okay, so this is my modulus of elasticity of column, and for M40 grade concrete beam, E value is given by 5000 under root FCK 41 by 2. Okay, so this calculation will come out to be 31622.77 MPa. Okay, so this is the modulus of elasticity of both column and beam. Okay, now we need to calculate the other factor, that is my summation IC by SH. Okay, so in this story you can see there are 16 columns: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16, and all column are of same size. So we have 16 columns of size 300 cross 300 So IC will be nothing but BD cube by 12. So 300 into 300 cube by 12. Okay, so this is my moment of inertia of column. So this will come out to be, so this is for one column. So total IC, summation IC will be 16 times this. Okay, so 16 times 300 cross 300 cube by 12. So this will come out to be, and since we need to calculate IC by SH, I will divide here HS also. Okay, so 600 300 into 16 into 300 into 300 cube by 12, and 12 multiplied by HS. So HS is 10 meters, so that is 10,000 mm. Okay, so this total calculation, if you will do, it will come out to be 108 into 10 to the power 4 mm square, mm to the power 4. Okay, millimeter to the power 4. Okay, so this is my summation IC by SH that I am getting for 16 columns. Okay, now for beams, this is same in both x direction and y direction because column dimension are the same. But for beam in both x direction and y direction, the ib value will change. Okay, so for x direction, beam dimension is 300 cross 600 and how may what is the length of the beam? Length of the beam, it is, you can see in x direction it is 6 meter. Okay, 6 into 3, so l is 6 meter. Okay, and how many beams are there? 1 2 3 4 5 6 7 8 9 11 12 uh, 10 11 12. Okay, so there are 12 beams. So total summation ic by ib by li, it will be 12 into moment of inertia of beam times the length of the beam in x direction. So it will be 12 into 300 cross 600 cube divided by 6000. 6 meter I am converting into, divided by 12 into 6000. So bd cube by 12. So that's why 12 we will need to divide at the denominator also. So once you will do this calculation, it will come out to be 108 into 10 to the power 5 mm to the power 4. So this is my moment of inertia of beam in x direction. Similarly, if we will calculate the moment of inertia of beam in y direction, so what will happen? I will just copy this segment and I will paste again. Okay, so in y direction, what will change? The dimension of the beam is changing. So in y direction, the beam dimension is 300 cross 450. 300 cross 450. Length of the beam is 4 meter instead of 6 meter. Okay, so I have, and number of beams are 12. So 12 into IB, so that is 300 into 450 cube by 12 and multiplied by this length. So length is, instead of 6000, we need to write 4000 this time. So this calculation, it will come out to be 683.4 into 10 to the power 4 mm 4. Okay, so this is how we are calculating the moment of inertia upon length in x direction and in y direction for beam. And for column, in both x and y direction, it will remain the same. Okay, so if I calculate now this delta u by v value, so it will again change in x direction and y direction. Okay, so I will subtract this whole part. Okay, so for x direction, so delta u by v value, so we know this EC, it is 35355.34. Okay, HS, we know the height of story, it is 10 meters, so we can write it as 10,000 to the power 2. Okay, summation IC by SH, we have calculated this, it is 108 into 10 to the power 4, so 108 into 10 to the power 4, that we have calculated. Here also EB we have calculated, it is moment of a modulus of elasticity of beam, that is 31622.77, and summation IB by LI in x direction, it is 108 into 10 to the power 5. Okay, 108. Wait, what is happening? Okay. 108 into 10 to the power 5. Okay, so when we'll do this calculation, delta u by v in x direction, it will come out to be 2.424 into 10 to the power minus 4 mm per newton. Okay, so this will come out to be in x direction. Similarly, if we do the calculation in y direction, the calculation thing will remain the same. So it is 10,000. Now just this column part will remain the same. Just in the beam part, this value will change. Instead of 108, we have 683.4 into 10 to the power 4. Okay, so just this calculation will change, entire everything will remain the same. So you will see the delta u by v value in y direction, it will come out to be 2.566 into 10 to the power minus 4. Okay, so this is in y direction. So we have calculated the lateral displacement in both x direction and y direction. Okay, now once we know that this delta u by v value, we can calculate the stability index. Okay, so for stability index, again I will copy this slide. Okay, I will delete this. I know the value of q, it is given by this. Okay, so I will copy this here. Okay, so for x direction, I will writing it as qx. Okay, so it is summation pu into delta naught upon summation vu into lc. So this delta naught upon vu we have calculated. So this will be pu net shear force, that vertical load that is acting, it is given that us to as 9,000 kilonewton. So this is nothing but 9,000 into 10 to the power 3 newton. Okay, multiplied by x direction. In x direction, we know this factor delta naught by vu, it was 2.424. Okay, into 10 to the power minus 4. Okay, and lc, height of story, we know it is 10,000. So 10 into and 10 meters, so 10 into 1000, so 10,000. Okay, so when you will do this calculation, the q value in x direction, it will come out to be 0.2181. Okay, so this is far more than 0.05. So we can say that it is unbraced frame in x direction. What about y direction? So again we'll repeat this calculation, just the delta not by vu value will change. Okay, so in y direction, if I calculate q, the stability factor, here I am just needing to we need to change this 2.404, it will be 2.566. Okay, so this value, it will come out to be 2 point, 0.2309. So this is also greater than 0.05. So what we can say, the column in the story, they should be considered as unbraced in both direction, because qx and qy both are greater than 0.05. Now once we know it is unbraced frame, so what we'll do, we need to use this alignment chart for calculating the effective length. Okay, and for this we'll use the second formula of beta. Okay, so this beta we need to calculate. Okay, so I will just copy this value of beta formula here. Now again, here I need to add the summation of ic by sh, ic by sh, and ib by lb. Okay, so again this value of beta, it will depend upon the direction, because ib will change in both the direction. So I will just give you the final value. So in x direction, in y direction, when you will do the calculation, beta value will come out to be 0.077, and in x direction, when you will do the calculation, beta value, it will come out to be 0.166. Okay, so once we know this beta value, using this alignment chart, we can calculate the k value. Okay, so from this, for 0.077, you can see it will be very close here. Okay, between 1.1 and 1.05. So from this you can calculate the value of k. So it will be around 1.03. So k will be 1.03. So 1.03 times the effective length in that direction will give me in unsupported length in that direction will give me the effective length, and effective length upon d will give me the slenderness ratio. Similar calculation you will do on the opposite side also, where the beta value is 0.166. So 0.166 will lie between zero point 0.1 and zero point 0.2, so somewhere maybe here. Okay, so 0.166 here, 0.166 here, it will be value something lying here in between 0.05 and 1, 1.05 and 1.1. So again, by interpolation it may come out to be around 1.08. So you can again calculate the L effective along that direction and then slenderness ratio along that direction. Okay, so this is how the calculation is done. Okay, any doubt in this entire calculation procedure, how we do the calculation, how we get the stability index value? Any doubt in this? So in exam, they may not give you this entire question. Okay, they may give you the dimension of beam and column, and they just may ask you to calculate the lateral flexibility or just to calculate the stability index. Okay, or maybe if the stability index is known, okay, it is a sway frame or a non-sway frame, they may ask by giving you the dimension of beam and column, they may ask you to just give the calculation of effective k. So you just need to calculate the beta value and then you need to use the chart. Okay, any doubt in this part? Okay, so now let's move ahead. So now we'll talk about design and detailing of RC column based on IS 456 codal provision. Okay, so for main reinforcement, what code says, or we can say main reinforcement or longitudinal reinforcement, these are reinforcement that run along the length of the column. Okay, and they resist axial and bending stresses, that we know. Now what IS 456 code says, it has posted different kinds of limits and criteria for main reinforcement. So what code says, the percentage steel in column shall be taken between 0.8 to 6% of gross area. So gross area is represented by AG, and steel reinforcement area is represented by ASC. So ASC should be in between zero point 0.8 to 6%. Okay. For pedestal, the which it we can design a plain concrete also, but with a minimum reinforcement of 0.15% of gross area. And for reinforced concrete wall, we need to keep the minimum reinforcement as 0.15 times gross area or 0.12 times of gross area if we are using wire mesh. Okay, so this is the criteria that code has mentioned for percentage steel reinforcement. Now code says that minimum 4 number of bars needs to be used for a rectangular column and 6 number of bars needs to be used for a circular column. So if I have a rectangular column, at least 4 bars I need to provide, and if I have a circular column, at least 6 bars I need to provide. Okay, the diameter of bar should not be less than 12 mm. Okay, that is one more limit. The spacing between the reinforcement should not be more than 300 mm. So how many reinforcement you are providing, this effective center to center spacing between the reinforcement should not be more than 300 mm. The clear distance between the bar should not be larger than 1.5 times the bar diameter or space or 40 mm. Okay, so this clear cover, okay, this will be clear cover. Okay, so that should not be less than 1.5 times the bar diameter or 40 mm. Okay, and at least 40 mm clear cover we need to provide. Okay, or the diameter of main reinforcement, whatever it is there. So these are different criteria that has been mentioned in IS code. Okay, for main reinforcement. And for transverse reinforcement, which are also known as tie bars, they run along the lateral dimension of the column and they function to hold the main reinforcement. So this we have seen earlier also. So for tie bar, code says that bar diameter should not be less than 1 by 4th of mean diameter or 6 mm. So suppose if mean diameter is 20 mm, so the tie bar diameter should be greater than 1/4 of 20, that is 5 mm and 6 mm. Okay, so we can use 8 mm bar diameter here. Okay, and spacing should not be more than minimum of 300 mm least lateral dimension of column and 16 times the diameter of main reinforcement. So based on these three values we will get the spacing. And for spiral columns where we are providing spiral reinforcement, the code says that the spacing between the spiral reinforcement, it should be less than the minimum of these two value, and it should be more than these two values. Okay, so there is spacing s that we are providing, it should be more than some values and it should be less than these values. So in between these two sets of value we need to provide the spacing. Okay, and for diameter we can again use the same clause that is given for tied column. Okay, so generally, when we talk about column, we either provide 8 mm uh, tie bars or 10 mm tie bars. These are generally that we use for transverse reinforcement. Uh, then, as we saw earlier in the discussion, there are chances that load is not acting directly at the centroid. Okay, so code says that all columns should be designed for minimum eccentricity. So irrespective of whether there is load acting at the centroid or not, we need to assume a minimum eccentricity is present in the loading. So for E minimum, code has given this formula L naught by 500 plus D by 30 or 20 mm, whichever is greater we need to use as E minimum. And for non-rectangular and non-circular section, this value is given by these two formulas. So based on the unsupported length, the length of the column, okay, and the dimension of the column, we calculate the E minimum value. Okay, so this minimum eccentricity we always needs to assume, and if this E minimum value it is less than 0.505 times the least lateral dimension, then we can assume it is actually loaded. Okay, so like what we saw earlier in the question, if this value is less than 0.05, it is can be assumed as actually loaded column. If it is more than 0.05 times the least lateral dimension, then we need to design as a eccentric column. Okay, now for axially loaded column, we assume that the ultimate strain value is 0.02. Okay, and since the entire reinforced concrete is under axial compression, so both steel and concrete, they will be subjected to same amount of strain. Okay, so since column is a compression member, both are subjected to same amount of strain, and the ultimate load carrying capacity of column is the sum of resistance provided by concrete and the sum of resistance provided by steel. So what is the resistance that is provided by concrete? It is 0.447 fck times area of concrete. And what is the resistance provided by steel? So it will be the strain corresponding to this stress corresponding to the strain value fsc times the area of steel reinforcement. Now generally we know the gross area of concrete. Okay, so gross area of concrete is nothing but uh, gross area of reinforced concrete is nothing but area of concrete plus area of steel. Okay, so if we don't know the area of concrete, we can write in terms of gross area minus area of steel. So generally when we do design, we don't know the dimension of column. Suppose we don't know the dimension of column, so what we assume, we assume some area of steel as 1% of gross area, 2% of gross area, whatever we want to assume. Then we calculate the gross area first. Okay, then we calculate concrete area. Once we know the concrete area, we calculate the dimension of concrete. Okay, we can calculate as a square column or a rectangular column, and we know the percentage that we have chosen. From that percentage we calculate the area of steel reinforcement. So this is why code represents this formula in terms of gross area and percentage steel reinforcement also. Okay, so FSC value, it will depend upon the grade of steel. For Fe4 250 it will be 0.87 Fy. For Fe415 it will be 0.79 times Fy, and for Fe500 it will be 0.746 times Fy. Okay. So now based on the grade of steel, this formula is changing. Okay. So what code did? just to simplify this formula, okay, so suppose this equation I have for Fe415 grade steel. Okay, so just to simplify this formula for any grade of steel and to take into account the effect of minimum eccentricity, what Coates did, it multiplied this Pu value by a factor of zero point 0.9. Okay, so when we multiply this Pu value of by zero point 0.9, code is saying that we don't need to change the formula for different grade of steel, and we don't need to account for minimum eccentricity also, and whatever Pu will get from this final equation, we can assume it is generalized for any grade of steel. Okay, so instead of FSC Fy for different grade of steel, we can just like this FSC value, which the factor which was varying for different grade of steel, we can just enter the final grade of steel here. Okay, so that is the simplification that code has done. Okay, now how we can provide this longitudinal bar and tie bars, they can also vary. Okay, so there are different schemes of design that is there in the code. Okay, so these are four schemes, this is the fifth scheme, and this is the sixth scheme. Okay, so based on the spacing between the bars and the dimension of the column, there can be different designs. You can see here, this is one tie and this is second tie. Okay, that is there in the beam. Then suppose it is an L column, so you can see this is one tie, this part, these four longitudinal bars are tied with this, then these four longitudinal bars are tied like this, uh, these four six longitudinal bars are tied together, and this six longitudinal bars are tied together. Okay, so like these different bars are tied with different types of tie bars. Then for spiral column, you can see it is circular ties that are provided. If the distance between these if there are more number of bars that are present, and we can arrange them like this also, concentrated near the corners, and tie bars are concentrated also near the corners. Then if the distance between two bars is less than 75 mm, then we don't need to provide additional ties for these two reinforcement sets. Okay, we can just tie the corner reinforcement and the middle reinforcements. Okay, if this entire distance from end to end is less than 48 times the diameter of the bar, then we can provide single strand ties for the middle bars. Okay, so based on the spacing criteria and based on the number of bars that we need to provide, different types of design can be done. Okay, so let's just see the application of this formula for actually loaded short column that we saw early recently, how we apply in terms of design. So this is the question that I have given to you. Just think how you will solve this question. I will mute myself for a minute and then we'll see the solution. In the meantime, if you have any doubt in this segment, you can ask, and just tell me how you will proceed along with this question. Okay, so can anyone tell me how they will proceed along with this question? We have been given the size of column, it is 450 cross 300. We know the unfactored axial load that is acting on the column. We know the unsupported length of the column, and we know that it is a braced column against, it is a braced against sideways. So along both the direction, it is braced. Okay, so we know all these detail, and we know we need to use M20 grade concrete and Fe415 grade steel. So what will the procedure?
So we will equate the equation Pu is equal to 0.4 FCKAC plus 0.67 FIAC,
But
in which
first
we
of
have
all,
all
do
the
you know whether it is a short column or a long column?
uh,
First we need to check whether it is a short column or not. Okay, right now since we have read only about short column, we are assuming that it is a short column, but in actual exam or in actual application you won't know whether it is a short column or a long column. So it is always a good practice just to give a initial check. Okay, once you have checked it is a short column, what you will do next? So then we'll check the eccentricity. What is the minimum eccentricity? And if that minimum eccentricity is less than 0.05 times the lateral dimension, then we'll say that we can design it as axially loaded short column. If that eccentricity is more than the limit of 0.05 times d, then we need to design it as eccentric column. Okay, so that check also you need to do. And then once you have done both these checks, then we'll design the column using that equation. zero point 0.4 times FCK AC plus 0.67 times FY ASC. Okay, clear?
Yes, yes, sir.
Okay, so we know the value of B, it is 450 mm. We know the value of D is it is 600 mm. Axial load is 2000 kilonewton. L naught value it is given to us 3 meter, and it is braced sideways in both direction. Okay, so it is a braced frame that we know. M20 grade concrete we need to use, that is known, and Fe415 grade steel it needs to be used, that is known to us. Okay, so step one is calculating the factored load. Okay, so always it is a good practice to check the question whether there is a factored axial load given or just normal axial load which is given. So factored axial load will be nothing but zero point 0.5 times the axial load. So zero point 0.5 times 2000, so it is 3000 kilonewton. Okay, that is my factored axial load. Okay, step 2 will be to check the slenderness ratio. So L naught is given to us. So L effective will be K times L naught. So K times L naught. Okay. But what is the value of K? That we don't know because end conditions are not given to us. We are just given that it is a braced frame. Okay, so we know k value will lie between zero point 0.5 to 1. Okay, in this range k value will lie, that we know. Okay, so without calculating the k value also we can check whether it is a short column or a slender column. How? So if I calculate L effective by D and L effective by B, okay, in both the sides, so this will come out to be k times L naught, which is 3 meter, k times 3000 divided by 450, and k times 3000 divided by 600. So it will be nothing but 6.67k and 5k. Now you see k value is lying between zero point 0.5 and 1. So at max this value can be 6.67 and at max this value can be 5, and both this value will always be less than 12. Okay, so even without calculating the value of k we can say columns are designed as short column. Okay, so without calculating, we got that sense because k value can maximum be equal to 1. And since this 6.67 and 5 both are less than 12, then always this will be a short column only, irrespective of whatever the end constraints we are providing, until and unless we know it is a braced frame. Okay. So this is the check that we have done for slenderness ratio. Now step 3, it is to check for eccentricity. Okay, so you will check E minimum in Y direction, it will be maximum of 20 or L naught by 500, so that is 3000 by 500 plus D by 30. So in X direction, in Y direction, D is my 600 mm, so 600 by 30. So when you will do this calculation, it is maximum of 20 comma 26. So E minimum in Y direction, it is 26 mm, and E minimum in X direction, it will be maximum of 20 comma 3000 by 500 plus 450 by 30. So it is maximum of 20 comma 21. Okay, just let me check this calculation. Okay, yes, 21. Okay, so it is 21 mm. Okay, so we know E minimum in X direction and E minimum in Y direction. Now what is 0.05 times D? So 0.05 times D is 0.05 times 600, that is equal to 30 mm. So we can see this E minimum in Y direction, it is less than 0.05 times D. Okay, and in X direction it will be 0.05 times 450, which is equal to 22.5 mm. So in both the direction, E minimum value is less than 0.05 times D. So we can say we can design it as axially loaded short column. Okay, so that check we have done. Okay, check for it eccentricity is over. Now, the next step is the design of longitudinal reinforcement. So, step 4 is design of longitudinal reinforcement. Okay, so how you will do the design? PU is equal to zero point 0.4 FCK AC plus 0.67 FY AC. So 3000 into 1000, that is my PU, is equal to zero point 0.4 into 20 into 450 into 600 plus 0.67 into Fy 415 into ASC, that is ASC. So when you will do this calculation, ASC will come out to be 3000 mm square. Okay, so assuming that I am providing 20 mm diameter rebars. Okay, so a number of reinforcement, how we'll get? N is equal to total reinforcement area 3000 divided by area of one reinforcement, that is 314 mm square. Okay, so pi r square, pi into 10 into 10, so this will be roughly around 9.55. So we will round it off to 10 number of bars that we will provide. Okay, so we'll uniformly distribute this 10 number of bars, and when you will calculate the percentage area, it will come out to be 1.2%. So that is lying between the limits that is mentioned in the code, 0.8 to 6%. Now, next step is step 5, that is design of lateral reinforcement. Okay, so how this design is done? Tire diameter, it is given by, it should be more than L naught by the diameter of longitudinal bar 20 by say 4 and 6. So 20 by 4 is 5, so 5 and 6, so we will provide 8 mm tie bars, and spacing, tie spacing, so that should be minimum of 300 mm, or what was the other criteria? 3 times the diameter of least lateral dimension of column, or 16 times the diameter of main reinforcement. So 300, I will copy this here. Least lateral dimension of column, that is 450, and 6 times the diameter of main reinforcement. Okay, so 6 times 20, no, this would be something else. 16 times the diameter of main reinforcement. So 16 times 20 is 320. So we need to provide a spacing of 300 center to center. Okay, so this is how we do the design. Okay, everyone are clear with this? Any doubt in this numerical? So first we check for slenderness ratio, then we check for minimum eccentricity, and then we designed it for axially loaded short column. Any doubt in this part?
No, sir, no, sir.
Okay, so now we will move to the last segment, that is there is a provisions for spiral reinforcement. For so based on clause 39.1 of IS 456, what code says that we need to enhance the loading capacity that we are getting by 5%. Suppose PU is the capacity we are getting for rectangular column. For circular column, we need to assume the capacity is 0.05 times PU. Okay, if we are providing spiral reinforcement. Why is that so? Okay, because if you see a rectangular column and a circular column, what happens, there are tied and spiral reinforced column of same cross section. The cross sectional area of both the concrete are the same, and in both the case it is actually loaded. Okay, steel is behaving similarly till the ultimate load. Okay, so at ultimate load, what is happening when we are talking about tight column, it will suddenly fail due to excessive cracking in concrete due to buckling of longitudinal rebars. Okay, however, in spiral reinforcement, once this ultimate load is reached, this point is reached, you will see that the concrete cover will fall off, but there will be no buckling in the reinforcement due to the spiral action that we have provided. Due to ties, they will confine the concrete core and they won't allow the steels to buckle, and thus the failure will be delayed. Okay, so instead of failing here, it is failing here now. Okay, because of the confinement effect the spiral reinforcement is providing, the steel won't buckle, and as it will reach the ultimate load, and thus it will be able to sustain more amount of load. Okay, so that's why this 5% increment is done when we talk about spiral reinforcement. That is the confinement effect. Now, how we determine this volumetric ratio of spiral reinforcement and confinement pressure due to spiral? So, code says that the spiral reinforcement ratio, it is given by this formula. Okay, rho s is volume of spiral upon volume of core. Okay, so suppose this is my reinforcement cross section and spiral running like this. Okay, or you can see from the plane view, this is my plane view and this is my plane, this is my plane view and this is my elevation view. So these are my spiral that is running. Okay, so volumetric ratio is the volume of spiral, that is nothing but the area of spiral times the pi times the diameter of this core. Okay, that is the volume of my spiral, and volume of core, it is nothing but pi by 4 d square times s. Okay, so this I am considering this small section, okay, of height s. Okay, where one single spiral is there. Okay, so this single spiral, it has an area of asp, and the length of the spiral, it is nothing but pi r 2 pi r. So that's why I've written it as pi dc. Okay, and volume of core in this region, it is nothing but pi r square h. Okay, so that's why pi by 4 dc square times h is my s. Okay, so this is how I get the spiral reinforcement ratio. Okay, and experimentally it has been proven that this fcc, that is confined concrete pressure, times the compressive strength of concrete, FCC minus FC dash, it is nothing but 4 times the F2. So F2, it is the lateral confinement pressure. So we can write FCC, it is nothing but FC dash plus 4 upon 0.85 times F2. Okay, so whatever strength concrete is having, the confined compression strength, it will be increased by this factor zero point 0.4 upon 0.85 times F2, and F2 is the confinement stress that is created due to the spiral. So this much increment the spiral reinforcement can do to the effective strength of column. Okay, now how we can get this relation between the force that is exerted by the spiral and the confinement stress that is generated by the spiral. So code has given this relationship: 2 times the area of spiral times the force that is generated by the spiral, it is nothing but equal to the confinement stress F2 times dc times s. Okay, so if you arrange this equation and use this confinement pressure relationship, eventually you will get this formula at the end. Okay, assuming that FCC is nothing but AG times FC dash upon FC. So this again one assumption is done by the code, and finally you get this formula. Okay, so what clause 39.4.1 one says that the spiral reinforcement ratio should be at least greater than this equation to ensure that there is effective confinement pressure that is created by the spiral, so that this experimentally proven equation follows. Okay, so this is what is happening when we are talking about spiral reinforcement. There is minimum spiral reinforcement ratio that we need to take care of. Then once we know the minimum spiral reinforcement ratio, we can calculate the lateral confinement stress that the spiral is bringing, and we know how much permissible load capacity is there for a reinforced concrete column when there is spiral reinforcement. So that is nothing but 0.055 times the pu value that we are getting for lateral reinforcement. Okay, so let's see one example in which all these three different calculations we will do. So we have a short concentric loaded RC column. So we, it means that E is equal to 0. It has the overall diameter of 400 mm. It is reinforced with 6 number of longitudinal bar of 20 mm diameter, uniformly arranged in a circle. The column uses a spiral reinforcement of 8 mm diameter that is given to you. Grade of concrete is given, grade of steel is given, and for both spiral and longitudinal steel we need to assume Fe 500 grit steel, and we need to assume a clear cover of 40 mm. So these are the four things that you need to calculate. Okay, design axial capacity of column, required volume of spiral confinement, required pitch spacing, and confinement pressure created by the spiral. Okay, so can anyone tell me how you will proceed along with this question? Did everyone understand what we are talking here? Any doubt in this final segment about spiral reinforcement? Can anyone tell me how you will do the calculation here now? What will be the first step? Okay, so let's see the solution. Okay, maybe after solution it will be clear to you. Okay, so first thing is that we need to calculate the axial capacity of column. Okay, so what is given to us? So we know the diameter of the column, it is 400 mm. Okay, So what we can do, we can calculate the gross area of column. It is nothing but pi r square. So 3.14 into 200 into 200. So this will give me the gross area. So it will come out to be 125,663.71 mm square. Okay. Now we know we are provided 8 numbers of 20 mm diameter rebars. So AC will be equal to 8 into 3.14 into 10 into 10. Okay, so this will come out to be 2513.27. Okay, now spiral is of 8 diameter. So we can calculate area of spiral. It is nothing but 3.14 into 4 into 4. So it is 50.27 mm square. Okay, and clear cover is of 40 mm. Okay, this is given to us. FCK, it is given to us, it is 30 MPa, and FY, it is given to us, it is 500 MPa. Okay, so first, for design axial capacity as per IS 456 code, PU is nothing but 1.05 times zero point 0.4 FCK, that is 30 times AG. So AG is given to us 125,663.71 plus 0.67 FY minus zero point 0.4 FCK times ASC. So ASC is given to us, it is 2513.27. Okay, so when you will do this calculation, the PU value, it will come out to be 432437.74 kilonewton. Okay, so this is the axial capacity of my circular column. Okay, from the spiral reinforcement that I am getting. Now, what is the required minimum volumetric ratio of spiral? Okay, so for this, we first need to calculate the core area, AC. So core area will be nothing but, for this we need to calculate core diameter. Okay, so core diameter DC is nothing but subtracting the cover. So total diameter is what, for 200 400 mm. So from 400 I will subtract the clear cover from both the side, 40 minus 40, and then I need to subtract the radius from both the side. Okay, so since diameter is uh, 20. Okay, sorry, I need to subtract the spiral reinforcement diameter from both the side. So it will be 8 minus 8. Okay, so this will give me a core diameter of 312 mm. Okay, so you see, core means this diameter, okay, which is enclosing this, all the longitudinal reinforcement and the center to center distance of the spiral. Okay, so that is my core diameter. Okay, so that's why 8 minus 8 I have done. Okay, and so sorry, without spiral reinforcement, whatever it is, the diameter that is given to us as core diameter, so that is 312. Okay, so ASC, it will come out to be 3.14 into 0.25 into 312 into 312, so it will come out to be 76453.8 mm square. Okay, this is my AC. Okay, so then based on this formula that we saw a couple of slides ago, I can calculate rho s value. Okay, so rho s will be given by this. So zero point 0.6 AG value we know, it is 25125,663.71. Area of core we know, 76453.8 minus 1. FCK, it is given to us, it is 30 and fyt will be 0.87 times fy. So it is 0.87 times 500. So this rho s value, it will come out to be greater than or equal to 0.06016. So this is the minimum spiral reinforcement ratio that we need to provide. Okay, volumetric ratio. Okay, so this is how we'll get the minimum volumetric ratio of spiral. Okay, for pitch, what is the pitch of this spiral reinforcement? So pitch, PS of spiral, it will be given by 4 times ASP upon DC into S. Okay, this will be the pitch. Okay, so rho S we know, so S we can calculate. It is 4 into ASP, which is 50.27, divided by DC, which is 312, into rho S. Rho S is 0.016. So in this way, S will come out to be 40.28 mm. Now we need to check it with minimum criteria. So this should be less than or equal to DC, or DC by 6, or 75 mm. Okay. So when you will calculate DC by 6, it will come out to be 52, and this is 75. Okay, so both of value that we have provided, it is okay, and this 40.28 should be greater than or equal to maximum of 25, or 3 times the diameter of spiral reinforcement, that is 24. So again, this 40.28 is okay for us, so we'll provide a spacing of 40 mm center to center. Okay, and what is the confinement pressure that is generated? So confinement pressure F2, it is given by rho s times Fyt by 2. So rho s times Fyt by 2, it is the confinement pressure. So 0.016 into 0.87 into 500 by 2. So when you will do this calculation, it will come out to be 3.48 megapascal. Okay, so this is how we do the design for spiral reinforcement. Okay, any doubt in any of the part of calculation here? So first we know the total diameter. Okay, from that we got the gross area. We know the number of rebars. So we got the area of steel reinforcement. We got the area of spiral reinforcement. We know the clear cover, and we know the FCK and FY value. So we calculated the design compressive strength of column. Then we calculate the core area from core diameter, and we use this formula to get the spiral reinforcement ratio. Once we know the spiral volumetric ratio, then we calculate the spacing of the spiral. We checked it with minimum and maximum criteria that is given by IS code, and then we calculated the confinement pressure of spiral. Okay, any doubt in this question, how we proceeded with the calculation of different part? Can everyone hear me?
Yes, sir. Yes, sir.
Okay, so this was all about today's session. Okay, we talked about basic classification of column. We talked about a calculation of effective length of column by deciding whether, by calculating the stability index. We talked about design of lateral tight columns. We talked about design of spiral reinforced column. Okay, thank you. Now, if